Hello everyone, this video is to show you how to do a one-tailed hypothesis test versus when you're dealing with the right tail or the left tail. So we've got our crop data from North Dakota, South Dakota, and Nebraska, looking at corn yield, soybean yield, and then the rental price for cropland. We've got a population of 20, where we drew a random population of 12. Though that random population is down here. And then we have our descriptive statistics for our population up here. So we're going to start with a right-tailed hypothesis test. So Excel can do this very quickly with what's called a z-test, or the z-dot test, which gives you the p-value of your one-tailed hypothesis test. So what we're going to start with is we're going to say our claim is that the average soybean yield is greater than 48 bushels per acre. So this is a one-tailed test because we're dealing with that greater than. Our null hypothesis is less than or equal to 48 because we always leave that equal to as the null hypothesis. So we are testing actually that less than or equal to 48. So how do we do this? Well, our first step is to look at that z-test alone. So this z-test is it's usable for the one-tailed test, but it's looking at, or it's more for when you're looking at the greater than. So keep that in mind because we are doing greater than. If we did less than, we'd have to do a little bit of manipulation to it, which we will get to. So z-test. So now we need to go to our array, which is back here because we're dealing with our soybean random sample array. And then we are looking at our x, which is the assumption. What are we assuming is true, which is that 48 right there. We're assuming it's 48 or less, even though our assumption is greater than. And then we need the sigma, which is your standard deviation of the population, which when you're dealing with your variables, you've got your 20 population, or your 20 element population, that's what you're looking at. So we need to get our standard deviation from there. Close the parentheses and hit enter, and we find that it's 0.986. So that's a p-value of 0.98. That's a really high p-value. And what that tells us right away is that we are not able to reject our null hypothesis. So that's what this test tells us. We'll see if we're right. So let's say fail to reject the null hypothesis. We'll see if everything else comes out right and we've reached the right conclusion. So that's the fast way of doing it, well, semi-fast. Now let's actually use givens and see how we do with the math. So let's see, we're going to merge and center and call this givens, starting with our sample mean. Then we're going to go into the mean of the sampling distribution, which is assumed to be true. So that would be the 48 that we are looking at. We then need the standard deviation of the population and the sample size. From there, we're going to calculate our z-test statistic, and then our p-value, hoping that we come up with the same thing. We also want to look at our critical z-score. We're dealing with a 95% confidence interval. We want to be 95%, so we're looking at a p-value of 0.05. So what that tells us is that when we look for that critical z-score, we can use the formula norm.s.inv. If we put in that 0.05, so that 5%, What that gives us is that negative 1.64 or 1.65, or no, sorry, excuse me, 1.64. Now, the issue with that is if you think about the distribution, that's the left tail. We want the right tail. So we can do that in two different ways. We can either put a negative in front of it, which will give us that positive, or we could do the 95th percentile instead of the 5th. Either way, you're going to get that 1.64 critical z-score. So now we've got to actually fill in the rest. So our sample mean. So this is our average of that array that we've already looked at, but we're looking at our soybean yield. We find that it's 40.475. So now the mean sampling, the mean of the sampling that we're assuming is true is that 48 that we were looking for over here with our claim. Standard deviation of the population, that's from these test statistics up here. Sample size is 12 because that's what we're dealing with. So those are all of our givens. Now if you look at the formula on page 389 of your textbook, that's how we get our z-test statistic. So we hit equals. This is a little long. We need some parentheses to make sure the order of operations is followed. So we're going to take our sample mean, subtract our assumed mean, close our parentheses. We're going to take that and divide it by our standard deviation of the population, and divide that, whoops, we need some parentheses there too, and divide that by the square root of our sample size, so of our 12, which is just B7. Close both parentheses, hit enter, and we get a z-test statistic of negative 2.2. Now, if you are thinking about what this standard distribution looks like, we've got a positive 1.6 and a negative 2.2 to z-test statistic. That should tell you that we are not going to, reject our null, because we're trying to find numbers that are on the right side of this 1.6. And obviously that negative 2.2 falls somewhere way over here on the distribution. But let's check our p-value just to see if we get the same thing as we got up here. Now, your p-value, the way Excel uses this is we're looking at a normal distribution. And so the p-value that, it's a little complicated because the p-value that Excel calculates with this norm.s distribution, looking at this p-value, or this z-test score, and then true, what that's going to tell us is the area to the left of our p-value, or of our critical value, so of our z-test statistic. So it's telling us that there's this much to the left of it. That's not our actual p-value. Because we're dealing with a right-tailed test, we need to take 1 minus that. So the real p-value is 1 minus that, if you want to do it that way, or if you want to do it all at once, we get equals 1 minus the norm.s.distribution with our z-test statistic and true. Because again, this normal sample distribution is telling us what's the area to the left of that z-test statistic. So either way, same thing. And that's actually what we got for our p-value from that z-test up above. So what this again tells us is that that p-value is really, really high. So we are going to fail to reject our null hypothesis. And because we fail to reject that null hypothesis, we are going to say that according to the sample, we do not have enough evidence to support the claim that the average soybean soybean yield is greater than 48 bushel per acre. So that would be our conclusion for a one-tail right test when we fail to reject our null hypothesis. So now we can look at another claim. We're just switching it around, same type of thing where we've got a soybean yield that is more than 34 bushels per acre. So we're still dealing with a one-tail test and a right tail test, looking at that right end. Except for now we're just using a different top number. We're using 34 instead of 48. So if we come back into our Excel and we change this here to a 34, things changed a little bit. And let's see if that would change up here. If we come into our formula and change that 48 to a 34, do we get the same thing? Yes, we do. So here, now again, let's look at these. Again, we've got our p-value down here. That one or that one you can look at, same as this one. But let's also look at our critical z-score and our z-test statistic. So if we look at that z-test statistic, you should be able to picture that that 1.9 is to the right of our critical z-score of 1.64. But again, if you just use that p-value there, or that z-test p-value, you don't have to calculate the rest of these. But what this tells us is that's a low enough p-value for our alpha, so we are going to reject our null hypothesis. So we can just take our conclusion, we're going to change it a little bit. So we are going to reject the null hypothesis. Because it's low enough, we have evidence that states that our that we can reject that null hypothesis. So according to the sample, we have enough evidence to support the claim that the average soybean yield is greater than 34 bushel per acre. Remember, we cannot say to prove that the average soybean yield is greater than 34 bushels per acre, but we have evidence to show or to support that claim. So that is a one-sided right-tailed hypothesis test. So if we go down a little further, we can look at a new one. This is a left test. So we're going to now claim that the average soybean yield is less than 30 bushel per acre. So this is, again, a one-tailed test because we're dealing with that greater than or less than, and it's a left test because we're dealing with less than. So we're going to come back here and we're going to try some new things. Basically, it's the same exact idea, but this z-test shows you that greater than. So it shows you that the sample mean would be greater than the observed values. So because we're going to use that same thing, here we've got to take a 1 minus because we're dealing with a left test. So 1 minus that z-test. And then we go fill out our array. Again, it's the soybean because we're dealing with soybean bushel, the soybean data. And we're looking at 30 bushel. So then we type in a 30, and I'm up here if you can't see it. And then our sigma, which is our standard deviation from soybeans. If you're following along with this z-test array, it's on page 397 and 398. 398 tells you that the sigma is the population mean. That is incorrect. It should be the population standard deviation. So there is a typo in the textbook. Then we close it and hit return. And we get a z-test p-value of 0.9989. So that's a really high number. So that should tell us that we are going to reject our null hypothesis of our average being greater than or less than 30. So let's see if we can get the same thing when we fill this out with our givens. right, so our sample mean, again, is going to be that average of our data set, our random sampled data set. So that 40.47, same as we had before. Now we're looking at 30. Our standard deviation of the population, again, we got to go back to our data set and go to those descriptive statistics up here. And our sample size is 12. All right, so this time when we're looking for our critical z-score, we don't have to put the negative or anything in it because we are looking at the left side of the distribution, the left tail, so we just click or type equals norm.s.inv, and we want that 5%. And I think we need a few more decimals here. For some reason it's not giving them to me. That's too many. There we go. Negative 1.64, because again we are on the left tail, so we are on that negative side. So again, we're going to calculate that z-test statistic using the formula on page 389, formula 9.1 equals, parentheses, so we keep our order of operations, sample mean minus 30, because that's our assumption, divided by another parenthesis, our standard deviation of the population, divided by the square root of our sample size. Oh, and I forgot that last parenthesis. They corrected it for me in Excel. So we get our z-test statistic to be a 3. All right, so that tells us that I think I said it wrong up here when I said we were going to reject. We are not going to reject our null. No, I said that right. Because that 3 tells us that z-test statistic is way higher than our critical z-score. So let's look at our p-value and see if we come up with the same thing. I don't know where that came from. So our p-value, we are going to be looking at equals that norm.s.distribution and our z-score, our z-test statistic, and our true. And we have the exact same value. So what that's telling us is we do not have enough data and enough evidence to reject our null hypothesis. So we come up with our conclusion. We're going to use this one again. So we are going to fail to reject our null hypothesis. So according to the sample, we do not have enough evidence to support our claim that the average soybean yield is less than 30 bushels per acre. So we are not able to reject that null hypothesis of being greater than or equal to 30. Let's do one more. Let's make one more claim here. I don't think I have another claim, so let's make one more. What if we do another left test? Let's do corn this time. Let's do the corn yield. And let's see, if we come in here, our corn average is 152. So let's just go around the average. Let's say is less than, actually, let's come over here. If we look at our data points, what's our mode? Oh, we don't have one. Our median's 150. Minimum's 100.8. Let's see less than 140. Now let's just do the median at 150 bushels per acre. And let's see if we can reject that or not. So we're going to come back to our two-tailed test, and we can just redo that z-test up there. So remember, it's a left test, and the z-test in Excel is used for the greater than, so we need to take equals 1 minus that z-test for the fact that we're doing a left test. Our array of corn yield. Our assumption is that 150, and then my sigma is that population that I have here, standard deviation. Close the parentheses. We're closer. Not as close as we were here, but we were closer there. What if, let's see, what if we change that to 170? Then we're good to go, because then it's 0.007, so 0.01. So what we would do here, actually, what about 160? 160 we could at the 10% instead of the 0.05. But, so if we wanted to say at the 90th percentile, we would be confident, but let's see, what about 165? There we go, 165. So let's do that. So what this is saying is that we are going to reject our null hypothesis and say that according to the sample, we have enough evidence to support the claim that the average corn yield is less than 165 bushels per acre. Now these are, again, keep in mind these are oversimplified because I have such a small data set and I was manipulating things to show what I wanted, but these are the types of hypothesis statements that you will come up with for this week's assignment. Please let me know if you have any questions on that, and your hypothesis statements for the end of your project are going to be a little bit more complicated than this. But let me know if you have questions.